Hi guys, this is Romain from romainjanil.com. Welcome to the sixth edition of CityEngine user meeting. Virtually, unfortunately, but hopefully it will be done in person live the next edition. Anyway, the title of this presentation is Rule Them All, and so yeah, let's roll. In the background you can see Cubos. It's a demonstration cube I made 2 years ago, and I wanted to show you at the fourth edition of CityEngine user meeting, but because of the pandemic it wasn't possible. It's a tiny demonstration gathering some of the environments I produced in the past few years. So as you may know, I'm specializing into the reconstruction of 3D environments, mainly for simulation, helicopter, plane, and so on. And then these 3D environments are used and displayed into with the help of real-time engines, Unreal, Unity, Unigine, whatever, even proprietary engines or IGs. So the main focus of this presentation is not specifically to have a clear look at the results, but more at the way it's done. And the way it's done is a very, 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 very specific process I developed along the years to be able to deploy and generate 3D grammars. When I say 3D grammars, it's a rule set coded in CGA into CityEngine, and then applied onto initial shapes. So this process has to be done automatically. I mean, when you are doing a continent or even a country or a very large city, it's not reasonable to tweak every building by hand manually, and it's more, let's say, convenient to develop some math strategies in order to be able to have a realistic result, whatever the input data is. So here onto that cube we have 6 environments. Here it's San Francisco. The generation is done on as basis as it's OSM data as input, so it's OSM vector data, and you have a result in 3D. So it's CityEngine which is making the 3D buildings out of the grammar and applied onto the 2D footprints. Here we are another tiny environment. It's Los Cabos in Mexico. So it's yeah, it's another one. If you go there, where are we? We are in Texas. So it's an area of in Texas. It's Corpus Christi, etc., etc. And at the bottom, it's Lagos in Africa. So let's leave this cube and have a closer look to the Texas environment. This environment was done entirely procedurally with 2D input data, so initial shapes in the CityEngine language, which were acquired by machine learning actually. So one of the difficulty of this process is that all these footprints don't have any attributes at all to start with. So the grammar itself has to handle the generation smarter enough in order to build something that is um, realistic enough. So here we can see you have some individual houses, some industrial buildings, some commercial buildings. So you can make the difference with your eye and identify that, let's say, this one or this one is done. Yeah, it's realistic. It's mid poly actually. So if we have a closer look, you won't see tons of details onto the buildings. But for flight simulation, it's good enough. So the grammar behind that, the 3D rule set in CGA, has to handle the way the buildings are derivated from the 2D footprints automatically. Let's have a look at another environment. So here we are now in the south of France. Let's have a little flyover. And you can see some different kind of buildings. Residential, uh, old ones, some buildings for habitation, for inhabitation, residential buildings, but like multiplexes. You can see some, let's say, not industrial, but offices building, etc. This environment was done with the help as input of 2D vector data. Those data are coming from IGN, so National Geographic Institute in France. Those data also can be found on OSM OpenStreetMap. So it's the data available on OpenStreetMap is a copy of IGN. This specific data is another, so it's another input, and it's also have some particularities. If I switch to CityEngine, so this is the same tile as we've seen in real-time engine. You can see here, let's say a building, another one, and another one. And connected to them, I mean not really connected, but just near them, you have some tiny footprints which have attributes actually. And the main difference between this one and this one is tiny attributes encoded as a wall equal something. So this one has a wall equal normally yes, so it's a building, and this one has an attribute wall equals no, but it's unfortunately not specified at all what it is. So you don't know, starting from the initial to the building and looking at the attributes, you actually don't know what it is. So if, in order not to generate some stupid tiny buildings just next to another one, you have to, in your grammar, to be able to look at the data and infer something that represents somehow the reality. Okay, so now let's have a look, have a closer look to these particular footprints, which is really representative of the way it's the grammar is done in order to make something actually realistic from the provided data. So here we have 10 footprints. It's probably something looking like individual houses in a row. So it's important that the grammar itself automatically generates something that looks like that. So if you look at the attributes, you see that there is an attribute called class count, and all the features have this attribute with a value of 10. There is another attribute, neg count. It's and I will explain what it is. It's actually self-speaking. So this one has an attribute value neg count of 2 and a class count of 10. So it seems that all these footprints are in a row, meaning that they are part of a cluster because they are touching themselves. And this one has a neighbor count of 1, meaning that there is no laterality at the moment in this grammar, but it's something that I will tackle in another version. So if we generate that, boom, you can see that it looks like tiny houses in a row, meaning that the ridges of the roof are oriented somehow correctly, and that their texture or the texture themselves are representative of something that we are looking for when dealing with individual houses in rows. So if I took this this footprint, if I take this footprint and go somewhere, if I take it away, as all these attributes, class count and so on, has been pre-calculated, it won't change. So this is something that I try to do now into more dynamic way directly into CityEngine, and to transpose all this pre-calculation and pre-process into CityEngine directly into the grammar, but it's require lots of occlusion tests and so on. And the problem with that is that there can be also some side effects, because when processing the data in tiles, you don't actually know if the if this building comes into a tile and this one is in another one, it will miss the calculation. So it's somehow more convenient to do that as pre-process done in a GIS tool. Okay, now let's have a look at another environment in order to demonstrate what can be actually done now into CityEngine with the help of the new arrays and sort indices and so on. And I trying to push inside CityEngine more and more calculation in order to be able to avoid pre-processing. So here, if I select that and generate, we are in the Faroe Islands. You can see that all the street edges, the first edges actually, I don't use street edges because it's it gives too many attributes, so it's not really helpful to do that with a shapefile format. Anyway, first edge is actually enough to start with, and then if I switch the generation on, you can see that the roof orientation and roof choice is done by the grammar itself. So you have some cool, nice flowing ridges roof here, thanks to this kind of new operator for the roofing, and it's better than a gable roof. If I select a shape, of course, uh, let's say this one, and actually move it, boom, you can see that the roof has changed because the grammar itself analyzed the shape, and thanks to occlusion tests and proximities and so on, and building and self-building of hedges arrays, it's the grammar itself adapts and seeing that it's better for an individual building, I mean not inside a row, to have a gable roof better than a ridge roof. So this is something that is cool now, and I will most probably deploy onto every grammar I code. Of course, if you select this building, it's self-adaptive. So if you make the footprints tinier, you'll see that you switch to a texture representative for house. If it's a bit bigger, it will go to an old building, and of course, if it's massive, you'll switch to something more clever, like a residential building. Another thing I implemented into the grammar is something actually needed for this particular part of the world. Here you can see the buildings, the shapes. Everything is sitting on a hill or mountain, so it's absolutely uneven. So the grammar has to handle that. And also there is a particularity that the buildings provided by it's a GIS buildings provided by the land authority of the buildings. They have sometimes these bizarre walls parts, very tiny. If I generate that, which can lead to odd results actually, because I think these tiny parts are shared party walls actually, and with that level of detail, it's most probably not necessary or clever to generate that. Okay, so if you have a closer look to these features, what I've done in the grammar is it's only a work in progress, but it will show you how it can help with this kind of problematic features as initial shapes. For the moment, there is a cut small part, so it actually analyze. No, it doesn't work. Enable. Yeah, it analyze the feature, so it's actually a loop at the beginning of the shape derivation. So generate is my first rule, and with an iteration. So you have iterate here, which is actually the number of small parts which is set by the the result of a convexify and sorting of the different value of the convexify. So for the moment, it gets rid of the small parts, but in a future version, it will generate, instead of a wall with windows, it will generate something more clever, like a small party wall or something like that. So in order to conclude that, yeah, it's more and more calculation done into CityEngine, circularity is done into CityEngine, of course the geometry area, the long ratio, the ratio analysis of the initial shape, lots of calculation of the different, and storing of and ranking of the different edges of the shape, be it at the start, I mean with the initial shape, or inside the model. For instance, the roofing, the ridge roof will adapt for certain geometry. One last interesting thing, I implemented it to this particular grammar, which will be most probably deployed onto other ones, is the capacity to handle some weird use case like this one. Here you have the first edge, which is set here. It's absolutely not the longest edge of my shape, but in this particular case I have a big dormer, a big gable dormer on the roof, and it's done with setbacks. So I want to be sure that the orientation of this feature is actually set on the longest edge of the polygon of the roof base. In order to do that, I rely also on shape analysis at this moment and compute with the help of comp-e functions, store arrays of longest edges indices, rank them, and compare that to the first array of the shape, of the initial shape that has been stored, that stored the initial edge of the feature. So whatever the form, the shape of my roof, it always be on the longest. Yeah. Okay, so now let's have a look at another use case. So this is another environment. It's in Singapore, made for a company called Luz Carter, and it was done with their 2D data as input. If I switch the terrain off and the generated models, you have another challenging technical problem that has to be handled carefully with the grammar. They provide footprints which have attributes actually of for the height of the building, but as you can see, the different part of the buildings are independent. So it's clear enough. If I go to another one, you will see that the different setbacks of the buildings or parts of the buildings are actually independent 2D data. So it has also, it was another challenge to tackle, because in order to represent things accurately as a 3D model, it's important to handle this unit as a whole building and not different kind of building stacked together. If I generate this, boom, the grammar is actually handling that pretty well, I think. So it's all done with a pre-process on the GIS tool. If you look at the different attributes you have there, and it was done before we have all these fancy stuffs in CityEngine with arrays and sorting and so on, sort indices and so on. So the data itself provided some edges. It's average ground level, so it's height above the ground level, and I had to pre-process the data in order to make some arrays, some lists with of value, reflecting all the parts of the buildings, and use that into the grammar to make something out of it. So this building has an average height of which is yeah 53 meters. This one is 50. So depending on the architectural style, here we are in Singapore, it's reasonable guess that this part with an above ground level higher than the other one is actually a part supporting the water tanks that can be seen inside inside this area. This one is a bit larger, but has a very bizarre shape. So there are also another thing that is done inside CityEngine to the grammar, which relies most of the time onto the circularity of the shape itself. So circularity, you can see here the formula, is something I rely on very often in order to get some clues about the complexity of the shape. So if the shape is really complex, it most probably be something like that, or if it's rather circular, it will be derivated as something else, etc., etc. So every time into the grammar, it's always a trade-off and a way of kind of shape analysis. So here we have another example. Those parts are smaller than the main building. So we have the height, we have a ranking for the heights, and we have also a ranking for the area, for the surface, the geometry area, which is also something that is very important, because even if these parts are higher, they are smaller than the main part. So most logically, those would be tiny protrusion, like something that can be found in the maybe elevator cages or so on. I don't know exactly what it is, but if in Singapore there is all the residential high-level buildings are almost done like that. So the grammar itself is here really adaptative and try to figure out, let's say, what a shape should be, and it's something that is really important to keep in mind when developing some specific grammars. So yeah, I think this is it, and thanks for watching, and see you next time.